Okay, so what I quickly wanted to cover was what I gave you somewhat cheekily yesterday for lab. Right? So yesterday, the second lab question asked you to generate random samples. So I'm actually quite happy that I gave you that first lab question. I thought it may be too trivial, but I think what it made you realize is what these distributions or histograms mean. Right? Every time I say histogram, you had a rough idea, but you didn't quite really see why that's a distribution and so on. So now I'm hoping all of you, when I say histogram of samples or when I say distribution, you understand what it means. How many samples are present in each of these little bins, right? So what we wanted to do was to generate samples according to this probability density function, right? Now, can someone tell me the easiest way we can generate samples according to this probability density? Has anyone solved it? Nobody solved it. Can you think of a simple way? Very intuitive. Forget about maths and all that. Just a very intuitive solution works very elegantly for this. But obviously, it's not very efficient. So if you remember the example where we were dropping pins onto this circle and then recording how many fell in the circle and out, there's no reason you can't do it here, right? So what I can do is I know my domain is 0, 1, right? I take the value here. Did I give you f of x equals x squared? So at 1, the value of this is also 1, very conveniently. So you have a unit square. Simply generate random samples in the unit square. So it's a two-dimensional. So you have a number of two-dimensional random samples. These, unlike the random samples you generated yesterday, with n equals rand of n comma 1, these are n equals rand of n comma 2. So you have a row and a column or an x and a y coordinate. So now you have two n random values where you have n two-dimensional points. Okay, now if you look at this, can someone tell me now how do you do it? Every time you generate a sample, right? So let's pick one of these. So let's pick this. What I do is I check. So this sample here, let's say it is xi, yi. Okay, now I check if yi, I compare it with f of xi. Okay. If yi is, in this case, greater than f of xi, then I reject this sample. That's not a sample that satisfies my condition. I just throw it away. If I then look at a sample like that, and I look at xj, yj, and I see that yi satisfies this, then I keep the sample. What happens at the end? At any particular small bin here, which was your histogram, right? You would have rejected all of these and accepted these. So any bin you take, you would have done this. Basically, you would have accepted any points here and rejected them here. So in the end, once you plot the histogram, you by definition will get the distribution. As you can see, it's very intuitive, is probably correct, and very easy to implement. This is called rejection sampling. Okay, and rejection sampling is very elegant in higher dimensions. It doesn't matter what your dimensionality is of the space. The only thing now is, instead of sampling to sample a one-dimensional space, we have to draw two dimensions. That was the main cost. Right? So if you are in a two-dimensional space and I gave you a surface as your PDF, you need to generate three-dimensional samples. So it's only d plus 1. If you have a d-dimensional space, you need to generate d plus 1, which is a constant, so it's probably not that costly. And then once you do that, all you need to be able to do is evaluate whether to accept or reject it. It's quite an elegant idea. But what is the... Yeah, somebody will give you a distribution to sample from. If you're given a distribution f of x to sample from, then it's a very elegant way to do this. Of course, you may not always have this, but then you don't know what you're drawing samples from, right? You'll just draw them uniformly. So either you have a distribution from which you want to draw samples, or you don't have one and you draw them uniformly. If you have it, all you need to be able to do is evaluate it. Because every time you take a sample, evaluate it, check if it's greater or less, and then decide whether it's. As an idea, it's very elegant. And it's used quite widely. But what is the problem with it? The problem with it is, depending on your function, you may have to throw away a lot of samples. So to generate n samples, we don't know ahead of time how many you need to actually generate. So if you generate n two-dimensional samples, you may end up rejecting n over 2, or you may end up rejecting all but 1. If you have a very peaky function, which is like a Dirac, you will reject every single sample except maybe the one that falls onto that, or maybe even, so in theory, 0. So you'll never be able to sample, right? So the downside is you may have a computational overhead of generating some number of samples, more than the number you need. So that's one of the problems. On the plus side, it is elegant. Easy to. Okay, that's one way. Okay, now, can you think of a different way to achieve this? Can you think, now that you have one way to achieve this, can you think of a different way to achieve this? So let me give you a clue. Let's say you have a PDF, right? Let me give you a clue that you might have to use its CDF, or cumulative density. So if this is G of x, this is capital G of x, equals okay. We're going to integrate here, and I'm going to put the x here, which means for any value here, the value of g is integral 0 to x1, and you keep doing that. As you move along this, you use this. Now can you think of anything? So the advantage of this, one of the characteristics of this cumulative density function is that when this function, so at any point here, that integral is nothing but what? It is nothing but the area under the black curve. Right? That area tells you what x1 is, right? Which means you integrate. So if you want the value of this red curve here, you integrate the black curve till that point. Okay, so what does that mean? As you go from here to here, necessarily capital G of x has to increase. You're only increasing the area. There's no negative values, so it will always increase. The other thing is, if this increases sharply, then the cumulative function increases sharply. If this increases very slow, then the cumulative function kind of tapers off. If this becomes 0, the cumulative function remains constant because the area doesn't change. Okay, now that I've given you all these intuitions about the cumulative density function, can you think of a way to sample from whatever PDF you want? This is not continuous. That is a cumulative distribution. C stands for cumulative. Continuous tells you what the domain is. If your domain is discrete, then the probability density function is no longer a density. It's called a probability mass function. So it's usually called PMF for discrete spaces. Similarly, cumulative mass function. Okay, so now, can you think of a way to do this? Okay. Okay. Yeah. Okay. Yes, but yeah, that's more or less correct, but you don't need to add. So suppose I draw n random values and I show them here. Instead of on the x-axis, I show the n random values here, right? These are random values drawn just like we did yesterday. What would the histogram look like? It would be flat, correct? So I'm going to show the histogram of these values like this, so you understand what I mean. It's just shifted. So we have drawn n random values here. They're equally likely to be anywhere. So your histogram is more or less flat. Then what I do is for each of those values, I will ask the cumulative density function where it maps to on the x. Now what would happen to this? In regions that are very steep, right? Even 2 points that are pretty close to each other, right? So even points that are far from each other will map pretty close. So if this was vertical, both these would map to exactly the same x. The steeper this is, the closer they're going to be. Similarly, in this region here, 2 points that are very close to each other will still tend to be very far from each other. So I can have two random samples that ended up very close to each other that will fall very far apart on the x-axis. What would that mean in the context of our sampling? It means that we will have more samples where this is steep. And where is that steep? That is steep where the area increases fast. So we will end up with more samples here and fewer samples here, because samples here will tend to be spread out and samples here will tend to cluster. So if you take a uniform measure here and push it through this, what are we doing? This is g of x, and these are random numbers y, so this is g inverse of y, right? This is the inverse. Because we're going from this y to x, is the inverse of g, and we're saying g inverse of y. So if we generate random numbers uniformly, y, so if you do y equals rand of n comma 1, and then do x equals g inverse of y, then x will be distributed according to g of x. Okay? But why do we need the cumulative function, right? So you can think of this. What we want is we want to know what is the probability of x being less than some value, right? So you can write it like this. So this g inverse of whatever we saw, right? We want to know less than x. What is the probability that this sample is less than x? Right? And this is nothing but, what is g inverse of that thing? So if you apply now to this, if I apply g on both sides, then I get g of g inverse of y less than equal to g of x, right? G is monotonic, so we can say that's true. And g of g inverse of y is simply y less than g of x, right? So we'll end up with y less than equal to g of x. We can simply restate that condition as this, right? This is nothing but, right? So this is nothing but g of x, right? Which means the probability of this is given by capital G of x. So the density is the derivative of that, which is g. Okay? Is the highlight of the proof, not the rigorous proof. I would say look up the rigorous proofs. But this is how you satisfy yourself that this actually works and is the I think this should be enough for your lab. If you have any questions, let me know. One of your lab exercises is to go back to yesterday's second question and implement it using both the methods we've just discussed. Rejection, sampling, oh yeah. So this is called inverse CDF method. So what is good about this method is that every sample you've generated is used. There's no wastage of sample. You're not rejecting anything. If you generate n samples in invert, you get this. What's the downside? What's the downside? How are you going to do the inversion? So if you're given a general f of x or g of x, if I gave you g of x equals x squared, then it's fairly simple. You may analytically invert it somehow. But if you're given some arbitrary distribution, inversion is not obvious. So you may have to resort to numerical methods to invert and so on, which makes it complicated. But imagine if you're in higher dimensions, it gets even harder, right? Like even you have a 2D distribution, then how do you choose what to do and so on? That would have been a very good lab exercise. But I think let's do things in 1D first, and once we can do them, we'll do stuff in higher dimensions. Any questions? If not, I think you're ready to go. You can now go to the lab. I'll be there once I disconnect all the stuff. And yeah. 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 Oh, yes. So that's actually an interesting question. So right now, actually, I should have mentioned this. Thank you. So right now, we assumed that all random variables were independent and identically distributed. This is usually called IID, right? Independent and identically distributed. They all were uniform, and no random value depended on the position of another random value. They're all independent. In some cases, there may be a dependency. So, for example, in jittered sampling, we had partitions or strata, and we chose one sample in each. These samples are not, they're identically distributed in that they're all uniform, but they're not independent. Because we know this is a partition, we know these samples should not be in that partition. Somehow, implicitly, which in a way that we cannot mathematically write easily, this depends on all of the others. This partition could not have been here. Because we know there is a partition there, there's going to be a sample. It could not have been here because, so somehow to generate this, we know that these partitions exist in the domain. And that introduces a notion of correlation, which means somehow there is a dependency between these two random variables. So once there is correlation, things become a bit more tricky, because now we need to look at not just the random variable under question, but also other random variables which could affect its position. So if you would like, so a typical way to address correlation is so if you want to look at correlations in a 1D domain, then you double the dimension. So if you want to generate xi somehow correlated with yi, then you look at a 2D domain, xi, yi. If they are independent, then the samples could be anywhere in that space, right? If they are dependent, the samples will be here or like this. This is positive dependence and this is negative. Now you can think of a Gaussian or whatever you want here, and that covariance matrix, which is your correlation, will tell you what is the difference. Now remember, this is not a two-dimensional sampler. This is still 1D sampler with pairwise correlation, which means in the end you get xi here and yi here, right? So if they are not correlated, then yi will not depend on where you sampled xi. If they are perfectly correlated, then yi will be at the same location that xi is. If they are negatively correlated, if xi is here, yi will be 1 minus this. Right? And if there's a covariance matrix that tells you, then it will be somewhere, depending on whether it's positive or negative, it will be in appropriately correlated regions. Right? Well, this is a bit tricky because once you introduce correlations, the set of samples that includes the union of these two is not necessarily uniform. If this is a Gaussian, you give a covariance matrix, and if that covariance matrix tells you that if x is here, y can have some distribution of being here, then suddenly the union of those two, even though x itself, only the x's may be uniformly distributed, just by virtue of introducing this correlation, you might have resulted in a non-uniform distribution. This is very common in data, that there will be correlations between parameters, variables, and things that have been measured. And if you don't account for that, and assume that because one of the variables is uniform, that the union is uniform, then you'll see all sorts of effects. So the set xi union yi not necessarily uniformly distributed, even though xi is. Okay. And that depends. If it is exactly xi equals yi or xi equals 1 minus yi, then you can show that there is some there's some results on what happens to the distribution. Good. Anyway, that you won't need for your lab, but does it answer your question? Yeah. Okay, good. So let's get to the lab now. Yeah, so maybe I can. So the lab questions, as I said, are in the folder. So in the first one, I've asked you to create what is called an anonymous function. I've given you a link. You can look up what that is. I've given you the function. You can simply copy paste this in MATLAB. If you're curious, you can look it up. And I asked you to analytically integrate it using the methods we discussed yesterday. I asked you also to use Monte Carlo, which is just uniformly random samples, the first strategy that we came up with, and calculate error and plot those slopes. So we want to compare these three strategies for the convergence rate, right? And we'll see which one looks good. So that's one, just so that you're on the same page when we do the other stuff. Obviously, it's a Monte Carlo estimator, so every time you choose n samples, you get one estimate. It's a random variable. Remember, we need expectation. So generated k times, and I said at least 100, many iterations, and then take the average. Okay. The second question is doing what we did yesterday about the sampling function. Yeah, okay. So if you haven't done the second thing yesterday, then try to do it using what we've done today. If you have done that, then you can do L4. Okay? And if you've not done one of these two, you can do it at home today. So that we will continue at the same pace. So in short, by tomorrow morning, it would be nice if you did the lab exercises of yesterday and the lab exercise of today. And then this is the homework for today. Okay, I put it here. Okay. So I've also put it explicitly in homework 2 in case you decide to do L4. So if you have done it already, then this is done. You can check it. And I've asked you this, which we asked earlier. So I just put that down there so we don't forget. I actually gave you the answer to that, but see if you can build it from first principles yourself. Questions? Okay, sounds good.